Physical World, Chapter 2, Section 1, Digging Deeper, Minerals, Types of Minerals. In the Investigate, you observe the properties of crystals and mineral samples. Crystals are solid materials. The particles of crystals are arranged in an orderly, repeating pattern. You then used observations and tests to identify minerals. Minerals have been important to humans for a long time. Early humans used red hematite and black manganese oxide to make cave paintings. People in the Stone Age made tools out of hard, fine-grained rocks. In the Bronze Age, people discovered how to combine copper and tin from minerals into a metallic mixture or alloy called bronze. Later, in the Iron Age, people made tools of iron. Iron is contained in minerals like hematite and magnetite. Fe is the chemical symbol for iron. Let me scroll up a little bit. Okay. Today, minerals are used in thousands of ways. Feldspar is used to make porcelain. Calcite is used to make cement. Gypsum is used to make plaster and wallboard. Iron and manganese, together with small amounts of several other metals, make steel that is used to make buildings, trains, cars, and many other things. Some kinds of clays and a number of other minerals are used in medicine. These are just a handful of examples of how minerals are used in our daily lives. Figure 1. The minerals hematite, red, and manganese oxide, black, were used by early humans to make cave drawings. Okay, let me scroll down a little bit. To be considered a mineral, a material must meet 5 criteria. Minerals are solid, not liquid. Minerals are solid, not gas or liquid. Minerals are inorganic. That means they are not alive and never have been. Minerals occur naturally. They are not manufactured. Minerals have definite chemical compositions. These can be expressed as chemical formulas, such as, okay, you got the different formulas. All right, minerals have a regular 3-dimensional arrangement of atoms. This is called a crystal structure. All right. Some minerals, called native element minerals, consist of only one element. See figure 2, which is right here. They're saying copper is a native element mineral, meaning that it consists of only one element. A good example is gold, which is often found as nuggets or pieces of pure gold, not combined with any other element. Copper, iron, and silver are other native elements. However, most minerals are combinations of elements. For example, quartz with the formula, it's made of silicon and oxygen. Okay, so for example, quartz with the formula silicon dioxide is made of silicon and oxygen. See figure 3, which is, okay, so there's quartz composed of silicon and oxygen, and then calcite, okay, which is this, is made of calcium, carbon, and oxygen. Okay, so there's your calcium, carbon, oxygen. All right, and that's, okay. Rocks are naturally occurring collections or aggregates of mineral grains. Some rocks consist of only one mineral. However, most contain several different kinds of minerals. Sometimes you can see the mineral grains, and other times they are too small to see without being magnified. Granite consists mostly of large crystals of feldspar, quartz, and mica, as shown in figure 4. Basalt consists mostly of tiny crystals of feldspar and pyroxene. Let me scroll down a little more. Rocks that contain valuable minerals are called ores. To remove the valuable minerals, the ore first has to be mined. Two methods of mining include surface mining and underground mining. After being mined, the valuable mineral is then separated from the rest of the ore. This is done through processes like crushing, sieving, melting, or settling through a liquid. Most metals and many important nonmetals are refined from ores. Valuable minerals are not found evenly in Earth's crust. Finding new deposits is an important first step in mining. The mining company needs to understand the properties of the minerals and the ores that contain them. In Figure 4, you see that granite is a rock composed of several different types of minerals. All right. The chemistry and structure of minerals. As you saw in the Investigate, minerals can be very different from one another. The reason for this is that all minerals have a specific chemical makeup. Minerals consist of atoms of one or more chemical elements. Atoms are the smallest unit of a chemical element that has all the element's properties. Each chemical element has different chemical and physical properties. The atoms in minerals occur in a regular three-dimensional arrangement. The atoms in almost all minerals are in the form of ions. Ions are atoms that have an electric charge. This charge is due to electrons being added to or removed from the atom. Electrons are particles that orbit around the nucleus of the atom. They have a negative charge. The ions in a mineral are packed together in a way that brings the ions as close together as possible. As a result, positively charged ions are in close contact with negatively charged ions. Objects with unlike electric charges are attracted to each other. These forces of attraction hold the mineral together as a solid. So in Figure 5, this expanded view of halite, which is sodium chloride, shows the orderly three-dimensional arrangement of sodium and chlorine atoms. So your orange atoms are your sodium atoms, your yellow atoms are your chlorine atoms, and this is sodium chloride, which is also called halite. Okay. Identifying minerals. The atoms in a mineral affect the color, shape, hardness, and other properties of the mineral. The way the atoms are arranged also affects the properties. Geologists use a variety of tests. Hold on, let me click out of here. Okay. Geologists use a variety of tests to describe, compare, and identify minerals. Some of these tests are simple. They can be done with simple equipment. In the Investigate, you tested mineral samples for hardness, luster, streak, and color. You also tested to see if they were attracted to a magnet. Cleavage is another important property of minerals. Cleavage describes how a mineral breaks when under stress. You may have observed this in your investigation. Other tests require special, expensive equipment. These include specific gravity, crystal shape, electrical conductivity, and reaction to acid. Hardness. Hardness is the resistance of a mineral to scratching. Mineralogists use a relative scale of hardness. It is called the Mohs scale and is given below. Okay. So this is a scale of hardness. And hold on, let me scroll down a little bit. Yeah, this is the scale. Let me just scroll down so we can see it. So it goes from soft to hard. So the diamond is the hardest listed on the Mohs scale. So going from soft to hard, you've got talc, gypsum, calcite, fluorite, apatite, orthoclase, quartz, topaz, corundum, and then finally the highest hardness on Mohs scale is the diamond. Each mineral in the scale scratches minerals earlier in the scale and is scratched by minerals later in the scale. Diamond with a hardness of 10 is the hardest natural substance known. The mineral talc with a hardness of 1 is the softest. The way to test the hardness of an unknown mineral is to scratch it with a material of known hardness. If the mineral is scratched, it is not as hard. If the unknown mineral scratches the known material, then it is harder. Here are the hardnesses on the Mohs scale of some common materials. Okay, so a fingernail has a 2.5 level hardness. An iron nail has a 4.5 level hardness. A knife blade, a little more than 5. Window glass, masonry nail, 5.5. And a steel file has a 6.5 level of hardness on the Mohs scale. All right. Another way to identify minerals is by luster. Luster describes the way a mineral reflects light. Luster is either metallic or non-metallic. Minerals with metallic luster look like polished metal. Non-metallic lusters are often described as glassy or vitreous, waxy, pearly, earthy, or dull. Pyrite and galena have metallic luster. Quartz and calcite have a vitreous or glassy or greasy, Quartz and calcite have a vitreous, glassy to greasy luster. Feldspar has a pearly luster. So figures A to D. So there's your quartz, there's your feldspar with a pearly luster, galena, metallic luster, pyrite, metallic luster. Okay, so there's your metallics, pyrite and galena. There's galena, there's pyrite, and quartz and feldspar. Quartz has a vitreous luster, or that also means vitreous means glassy. And then feldspar has a pearly luster. All right. Streak. Streak is the color of the powdered mineral. To determine the streak of a mineral, scratch it across a piece of unglazed porcelain tile. A streak plate. Many minerals have a distinctive streak color. Streak color may be different from the color of the mineral sample. For example, hematite is often dark gray in color, but it always has a red streak. Some minerals are much harder than the porcelain tile and do not leave a streak. Avoid scratching the tile instead. Specific gravity. Specific gravity is a ratio of the weight of the mineral to the weight of an equal volume of water. Water has a specific gravity of 1. Galena is a mineral that contains lead. It has a specific gravity of about 7.5. That means that it is about 7.5 times as dense as water. Most nonmetallic minerals have specific gravities less than 3. These include minerals such as quartz, feldspar, and calcite. Cleavage. Many minerals have cleavage. This means that when they break, they tend to break along regularly oriented planes of weakness. Cleavage planes form along planes of weak atomic bonds in the mineral. For example, mica splits easily into sheets because there are very weak atomic bonds between the layers of atoms in mica. Galena and halite break in cubes because they have cleavage in 3 directions, all at right angles to one another. Feldspar has cleavage in 2 directions at nearly right angles. However, it breaks irregularly in other directions. Some minerals, such as quartz, have no cleavage. Quartz breaks into irregular shapes. It often shows a curved surface called conchoidal fracture. Okay, so in figure 7a, muscovite has 1 direction of cleavage. Figure 7b, halite has 3 directions of cleavage. They are at 90 degrees to each other. In figure 7c, calcite has 3 directions of cleavage. They are not at 90 degrees to each other. In figure 7d, feldspar has 2 directions of cleavage. The ways in which atoms are arranged also affects mineral hardness. For example, graphite and diamond are both composed of the element carbon. In diamond, the carbon atoms are arranged in little pyramids called tetrahedrons that fit together with very strong bonds between them. As a result, diamond is the hardest mineral on Earth and will scratch all other minerals. In graphite, the carbon atoms are arranged in sheets that resemble the pattern of chicken wire. Each sheet is stacked on top of another. The bonds between individual sheets are weak, allowing them to break easily when rubbed on a streak, plate, or a piece of paper. Okay. In Figure 8a, quartz crystals grow in hexagonal columns. In Figure 8b, garnets often grow in dodecahedral shapes related to the cubic crystal system. Crystal shape. When minerals grow in unconfined spaces, let me scroll down a little bit. Crystal shape. When minerals grow in unconfined spaces, they usually have a regular crystal shape. Quartz crystals grow as six-sided or hexagonal columns with pointed tops, which can be seen in Figure 8a. Let me scroll up a little bit. Okay, so they're talking about quartz now. Garnets often grow in regular 12-sided shapes. Okay. These shapes are called dodecahedra. Okay, right here. There are 7 basic crystal shapes. Okay, now we're talking about this figure. So where it says there are 7 basic crystal shapes as shown by Figure 9. Crystals are described using 2 different measurements. The lengths of the crystal edges, A, B, and C, are compared to each other. The angles between the crystal faces, as described by alpha, beta, and gamma, are also useful for defining crystal shape. 7 basic crystal systems: cubic, tetragonal, monoclinic, triclinic, orthorhombic, hexagonal, rhombohedral, and then these are the different minerals that are connected to those crystal system shapes. In Figure 9, minerals can be categorized into one of 7 basic crystal systems. Perfect crystals are rare in nature. If crystals grow into one another, it is possible crystal faces will not be well formed. Color is usually the first thing you notice about a mineral. However, it is the least reliable property in identifying a mineral. Many minerals have different colors depending on what impurities are present. Corundum, and here's the formula for that, is sometimes tinted red by small amounts of chromium. These crystals are known as rubies. Oh, I need to cut my, I gotta cut my alarm off. I have a meeting in 5 minutes, but that's okay. We're gonna keep going. Okay. A sapphire is the same mineral tinted blue by small amounts of titanium. Quartz is usually transparent. However, it can be many other colors depending on what impurities are present. Some minerals tarnish or change color when their surfaces are exposed to air. Many minerals have the same color as others. Many prospectors in the gold rush days were fooled by pyrite. Pyrite is known as fool's gold. It has a metallic luster and a color similar to gold. However, it has a lower specific gravity than gold. It is also brittle, gold is malleable, and leaves a black streak on a white porcelain tile. Gold has a gold-colored streak. Okay, so that's how you can tell the difference between gold and fool's gold, which is also called pyrite. Other properties. Some minerals have Some minerals have special properties. These make them easy to identify. They also make these minerals useful for specific purposes. Metals have properties that make them useful in machinery. Most metals are malleable. This means that under pressure they can be changed in shape without breaking. Also, metals are very useful in the production and distribution of power. Metals tend to be good conductors of electricity. Most are also ductile. This means that they can be stretched into wire. Some minerals have a chemical reaction to acids. Carbonate minerals are an example. They fizz when a drop of weak hydrochloric acid is applied. Acid breaks down the chemical bonds in the carbonate. The fizz is CO2 or carbon dioxide. So the fizz is carbon dioxide gas being released. Acid is a good test to identify the calcium carbonate mineral calcite. A few minerals are radioactive. The atoms of radioactive materials are not stable. They release subatomic particles and radiation as they decay. Uranium minerals are radioactive. They can be detected with a Geiger counter. This is an instrument that detects radiation. Some minerals are magnetic. Magnetite is an important ore of iron. It is magnetic. Some minerals are fluorescent. They change ultraviolet light to other wavelengths. Fluorite is one example. A few minerals are phosphorescent. They store light energy. Then they slowly release it.